I gave a talk yesterday at MIT, and it was kind of fun to talk about the heliosphere for people that are not used to hearing about the heliosphere.
At MIT?
Yeah, in the physics colloquium, they asked me to give a talk, and
so it was a colloquium, not
with
a
a colloquium, right? And was general, was for physicists, so it was fun.
Did you have fun?
I had a lot of fun.
I saw your video with the auditorium. That was big.
Did you see that? It was so
Yes, I
big.
did.
Like when I came, they said this is the biggest auditorium of MIT. I said like, oops. So first time. No, I'm sure it's not the first time, but they are not familiar with the heliosphere. So I was like, let
Now
me
they
introduce
are.
them. Now they are.
Now
Yes.
they are.
Now they are.
So thank you.
No, there were some people there I talked during the day that do exoplanets. I was so excited. I was like, when you look at exoplanet, they're within an astrosphere. Just think about it. And they gave some great ideas.
Are we live?
So, folks, we are live. What I will do is 2:00 because I don't want to pass the hour and I want to have enough time to you guys. I will start my short presentation. Welcome everybody for another installment of SHIELD webinar. For you guys to know, it's not only the audience here, but I know for many other sources, people come back to our website and check previous webinars. So it's something precious that we are recording that. Okay, so what I will do is just to give you a quick introduction. So this webinar is part of SHIELD, that is a NASA Drive Center. I'm the director, and John Richardson out of MIT is a program manager. And we decided a couple of months ago to start this new series of webinars inspired by, if you remember in NPR, there is a StoryCorps capturing histories. And we felt that Voyager it's prime for that. There's so many histories and stories and luminaries in our field that their stories need to be captured. And we thought that would be amazing to have Tom come back and discuss his story from the beginning of Voyager and have his story, how he mentored and how Kostas, passing the baton to the next generation, Kostas Dialynas pass the baton and the knowledge from what Voyager had at the beginning, and what we learn in all this lifetime exploring the solar system from the outer planets to right now we are in the interstellar medium. So just to remind, I'm sure everybody here on the call know that we live within an astrosphere. Stars are not naked creatures. They live within bubbles called astrospheres. We have our own habitable astrosphere, and you probably all have seen our movie showing how the heliosphere extends beyond all the planets and engulf our solar system. I'm not going to talk about all the activities of SHIELD. You can check our website. There's lots of things we're doing. SHIELD stands for Solar Wind with Hydrogen Ion Charge Exchange and Large-Scale Dynamics. And the team is big. It's not just national, but we have international collaborators, very important, like Kostas here of the Academy of Athens, and we have also people in Russia and in Bern collaborating with us. And it's a team of observers and theoreticians, modelers, and our goal is to create a digital twin of the heliosphere. In the sense, we're trying to understand all the processes driving the heliosphere so we can predict how the heliosphere reacts and will be in the future and how it was in the past. We also have a keen interest in making our team excellent. So we have lots of activities on bringing excellence in space physics. We have RUs, webinars, we have a summer school, we have coffee chat. So if you're interested, just check our website. There's lots of things we're doing that you can participate and be part, even if you're not part of SHIELD team. And our next event will be talking about, today we're going to talk about particles in space and the story that Tom and Kostas are going to share with us. And we are going to have in March 21st, John Belcher and Ralph McNutt talking about PLS and 50 years of plasma measurements. It will be another piece of the Voyager StoryCorps. So join us. You have the QR code here, and I'm sure Nick Ross, that is helping me here, is going to put on the chat the registration for that. So without ado, I'm going to pass the baton to Tom and Kostas. You guys have the stage. You can decide who goes first. It's very informal. I bought my coffee, so you can interrupt them, ask questions, and we can have a lively discussion at the end.
Okay, great. So thanks, Marav. Let me close my video and start sharing to save some bandwidth. And okay, so hopefully you can see my screen now. And you can see the presentation in full screen mode?
Yes.
Great. So I know.
Okay. Now I can see it. You were late.
Okay. Well,
Okay. So
so
thanks
I know
very
we have-
much. Go ahead, Kostas.
Yeah, you said it's going to be quite informal, but we decided to also have a first page at least showing Voyager because let's face it, we like it. So here is Voyager, and we wanted to have also the webinar title. So this is going to be the topic for today, and I think you're going to start with this picture.
So, yeah, thanks, Marav, for the invitation to organizing all of this. I thought I would share some slides, and this one is kind of a historic slide because I believe it was the first meeting of the Science Steering Group at JPL in 1972. And you can see
I'm not
various
recognizing
people.
you, Tom.
Say that again.
I am barely recognizing you, Tom.
There you go. Here he is.
And then you see Herb Bridge, the PI of PLS, and the original PI for the CRS was Robbie Vaught, not actually Ed Stone, believe it or not. And then the other person that is noted here is, of course, Norm Ness from the magnetometer. There are several people in this picture that are not just PIs, but JPL officials and program people. Next to Ed Stone is Bud Surmeyer. He was the first program manager for Voyager. Anyway, one of the people that you don't see is Fred Scarf, the late Fred Scarf, who was, as you know, the PI for plasma wave, PWS. And that is because in the initial definition phase of Voyager, the PWS was not included, and instead there was this dust experiment. That's a fellow by the name of Soberman. I think he was from Penn State, from the second person from the right.
Yeah, this
during
person, right?
Yeah, right. And during the validation phase of the program, his instrument was kicked off, and the PWS became the plasma wave instrument with Fred Scarf and Doug Garnett. And
Who is the gentleman standing next to Ed Stone with the red?
That's von Esselman. He was a guy who was the person that had to do with the occultation experiments of the radio science team, basically the leader. And at that time, there was it was an investigation that looked at the signal going through the upper atmosphere and ionosphere of each of the planets and deduce the electron density and so on and so forth. That was von Esserman from Stanford.
So that
So,
picture was in 1972, so before the
yeah.
Voyager launch, and it's the first science steering group meeting.
That's right. In fact, one of the things that I probably most people don't know is that the first program scientist was Ed Smith, the late Ed Smith, and for various reasons, with discussions with headquarters and so on, eventually Ed Stone was named the program scientist. And as I said, Robbie Vaught was the CRS principal investigator. So I think that kind of goes on to the next picture. Now, I'll say a few things about LECP. If we can go on the next slide, Kosta.
I think I advanced it. Can you?
I don't see it.
Really?
I see it.
Yeah, I see you, LECP, and the Voyager.
Well, I
Is
don't
that what you?
see. I don't see the slide.
Is that what you're looking, Merav?
Yeah, so I see Tom standing in front of the full-scale Voyager model.
Okay.
Well, I don't see it. For some reason, even the second slide was very late in coming to me. I don't understand that.
Maybe we
Listen,
should. Do you want?
oh, now I see it. Okay, now I see it. But it took so long. I don't understand that. Anyway,
Okay. Hopefully it's going to be fixed.
that's LECP that is labeled. I just wanted to show that picture and standing next to the spacecraft for calibration point on the size. By the way, the spacecraft was about 825 kilograms for those of you who are recent comers to the mission. Maybe you can go ahead and show the next one, Costa, if you can.
Yep.
But I see that if we have a problem, what we might do is maybe I'll use my version and I
Yes.
start sharing.
I'm
You moved
guessing
it?
you have. Yes, I did.
Okay, now, so now you see the instruments that are in with a yellow
Yes,
label
yes,
that are
yes, yes,
currently
yes,
operating.
exactly.
And you can see the teams. Adam Zabo is the leader of the MAG team. Bill Kurth, R. Cummings, John Richardson, as you can see. And the next one shows the zeroes in on the LECP. Okay, I'm waiting to see it if I can.
I changed it.
Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10.
Oh, it takes a long time, apparently.
10 seconds. So, simply to point out that the instrument is hanging on this science boom, so-called, and of course, as you can see, the antenna, the tip of the antenna is pointing at Earth. And so when the spacecraft is pointing at Earth, the solar direction is blocked by the science boom. And you will see why that is the case in the next slide. Go ahead, Kosta.
Yep.
This is sort of ridiculous that it takes this long. Okay, I think it's speeding up a little bit. So what you see on the in the inset is the proposal team, and you see people like Armstrong, Axford, Bostrom, Gleckler, Fan, myself, and Lanzarote. And as you know, we have already lost 3 of these people. You see the basic elements of the instrument, and you see on the right where it's hanging on the spacecraft. And that's where the sun shield is. I don't know if you can point, Costa.
Yes.
The sun shield is there, as well as the in-flight calibration sources.
This one and this one. Yeah.
Yeah, it's an electron source and an alpha source. And this way, we were able, every time the detector heads go pointing to the sun direction, as you can see from the inset on the left, it rotates through 8 sectors. And in one of those directions, it goes behind the sun shield. And what that does is it gives us a calibration throughout the entire chain from the detectors to the amplifiers and discriminators and so on. So, and that ability to really scan through 8 sectors, by the way, was near the ecliptic plane throughout the mission, not exactly at, but very close. That gave us a lot of very valuable information. The next slide, you will see one of the things that I want to point out.
But before we get to that, was it popular back then to actually have instruments rotating?
Of course not. I'll get to that when we talk
Okay,
about
I'm sorry. Yeah.
how many times, how many steps we got out of this.
Okay, so let me advance
Okay,
to the next
go
slide.
ahead. Maybe you can anticipate in advance before I finish talking about the slide.
That's what I'm thinking of doing.
I've seen
This
these
is
pictures.
ridiculous.
They're so cool, these pictures.
Everybody else is looking at the assembly of LECP right
Okay.
now. Okay.
I wanted to show you the platform over which the instrument rotates. That's above there on the left. And what you see in there is a bank of capacitors underneath it. If you can click again, Kosta.
Yep.
So you might say, this is archaic. What in the world are those? Those are catalytic capacitors, 48 of them, 270 microfarads. And we were charging those directly off the spacecraft 30-volt line, because to move the stepper, you had to hit it with a pulse of 15.7 watts. And it moved in a few milliseconds. So it really almost instantly from one sector to the next, 145-degree sector to the next. So that is the device. If you go to the next one, you might actually hear, if I remember correctly, the racket that he made.
This is a scale model of the Voyager 2 spacecraft that is presently in the process of flying by the
I didn't hear the rotation, Kosta.
Well, it was there. I'm
was
pretty sure
there?
everybody, yeah, everybody else heard it and saw you explaining the.
Okay.
Kostas,
So
can
yeah.
you do it one more time?
Yes.
Yeah.
Yeah. Sure.
okay, I think.
Yeah, very
This
cool.
is a scale model of the Voyager 2 spacecraft that is presently in the process of
Okay.
flying by the
If you cut down on the
Medium.
sound, look at the text there. It was designed to operate for 4 years, and from Jupiter to Saturn for the so-called Mariner Jupiter Saturn 77 mission. And it was expected to go 250,000 steps. So far, it's been 47.5 years, and it has gone more than 8.5 million steps. And for the last 4 years, because we had to save power and we turned off the heater, it's a minus 61 degrees centigrade. When we were getting back the first date after we sent a command to turn off the heater, I was expecting that we wouldn't see any movement whatsoever. And I almost passed out when I saw that the stepper motor was still stepping every 192 seconds. Didn't miss a step at minus 61 degrees centigrade. Needless to say, we never tested it for that. Next, please.
Yeah.
So it's an amazing machine. I can't believe it. It's working like that.
And I think you still owe us the story of how popular it was for instruments back then to rotate.
Yeah, if there is time, I'll reiterate that at the end.
Okay.
So you go ahead, and I think it's your turn now to say. a few
Okay. Well, it's the trajectory. I don't know if you want to say anything about the trajectory about the Voyagers, but of course, as you know, the missions were launched essentially in 1977, and there's actually one thing that probably you can answer: why Voyager 1 was launched after Voyager 2.
Well, it was obvious because it was on a faster trajectory, even though Voyager 2 launched on the 20th of August. It was on a slow trajectory because
Yeah.
we always intended for it to go to Uranus and Neptune, but we couldn't admit to it. So,
Right. So yeah, I mean, they were launched in 1977, and then they passed through the major planets of our solar system. I mean, they gained sort of velocity because of that, and I think that was a fairly new technique for the time, right? Getting gravity assist from planets.
yeah, it had been tried for the Mariner 10, the mission to Mercury that JPL did, and went by Venus and got a gravity assist and got to Mercury. But
Yeah.
the Voyager was by design, the so-called Grand Tour that the graduate student at Caltech had studied and invented with the help from a trajectory person from JPL whose name escapes me right now.
Right. So this plot here essentially shows the radial distance, the helioradius of the two Voyagers as a function of time since launch, and you can see, and also the latitude on this axis. And of course, Voyager 1 was essentially directed north of the ecliptic, and at some point, Voyager 2 was directed south of the ecliptic. And one of the things that I think it's pretty amazing is this plot over here. On this axis, you can see the intensities of ions of energies of a few MeV that you can see there, 0.14 to 0.22 MeV. The white lines is Voyager 1, the blue lines is Voyager 2, and these are the intensities, and the x-axis, of course, is time. And one thing that is very important about this plot is that this shows the intensities of these ions since launch all the way up to the heliopause crossing. So it's for this case 40 years, and of course we keep going and we have more measurements. And you can see there's a decrease, a general decrease of the intensities of these ions in interplanetary space.
And it's a logarithmic scale, by the way.
Of course, yes, that's a logarithmic scale, right? And there's a decrease in the intensity with some variation, of course. And then at about the year 2000, you sort of hit rock bottom here. I mean, how did it feel? Did you feel like you're losing the instrument or something?
Well, no, we thought, there was nothing more. I mean, we hit background on most of our channels.
Yeah, that's what I thought.
But you didn't expected it, right? Or was it a surprise?
No,
you didn't.
we didn't. I mean, it was, you get away from the sun and drops off, and it's 1 hour squared, and we were at the bottom.
Yeah, but then you had that part, the intensity started increasing as if it was a source in front of you, right?
Yeah, yeah.
So that gave you confidence, I guess, about what's coming. And what was coming was this part. Yeah, go ahead, please.
That was dramatic. to say the least.
Yeah, and Voyager 1 essentially was the first spacecraft to cross the termination shock at this point. That was in December of 2004, and then it entered the heliosphere, which is essentially a region between the termination shock and the heliopause, which serves as the or part of the interface between a solar bubble and the galaxy. And it stayed in the heliosphere for many years until it exited in 2012, a few years later, and this is the exit where the intensities of these ions dropped to nearly background levels. And then a few years later, the same thing happened with Voyager 2. Voyager 2 crossed the heliopause. This is where, the termination shock. This is where Voyager 2 crossed the termination shock. It stayed in the heliosphere for a few years, actually a little bit longer than Voyager 1, and then it crossed the heliopause in 2019. Now, during that time, and this is also very important, we were able to measure the cosmic ray ions since launch, so from Earth, all the way up to the very local interstellar medium, which is this part. And one thing that it was the first time that we realized it, I mean, measured it, because we thought about it, but we measured it, is that the heliosphere and the heliosphere actually protects us from these galactic cosmic rays, from these energies, by a factor of 7. I mean, the intensities at Earth drop at a factor of 7. And one thing that is also important to note is that there is an anti-correlation between the intensities of these galactic cosmic rays and the solar cycle that is labeled at the bottom. So you can see these are measurements that span over full 4 solar cycles. And of course, we have more measurements. And one of the things that, I always like showing this schematic, even in any talk, science talks or public talks or whatever, because this is one of a kind. I mean, we have New Horizons right now that it's serving, it's probably going to get close to the termination shock at some point, and it's making a similar plot to this one. But I'm not sure if it's ever going to be taking measurements from close to the heliopause. And so the next time we will be able to see something like that is going to be with an interstellar probe. And that's going to be in 30 years from now, if it moves forward, or maybe more. So I think this plot and any kind of plots that you see with Voyager measurements from all the instruments from PLS, LECP, CRS, and whatever, is one of a kind at this point. So let me move forward.
Just to add a quick, we're
Yes.
having a discussion if this, this bottom that Voyagers measured, is it something universal or not? It's a characteristic of the heliosphere. So those are unique measurements. Yeah,
and they sparkle a lot of discussion. I mean, even in a broader audience. I mean, in people that are interested in astrospheres in general, because let's face it, we don't have in situ measurements until in the foreseeable future, at least in other systems. So this is the only thing we can. This is our laboratory. So it's important. So I don't know if you can see the next plot now.
Yes,
with
Yeah.
the galactic cosmic rays. Good. So you can go ahead and explain that, because that was a
that goes after we crossed, as you all know. This was published a year after the original discovery of this first decrease was in our science paper in 2013. And it so happened that the sectors, the directions that dropped out, were the solar direction and the anti-solar direction, with the magnetic field being perpendicular to the radius vector. So that was amazing. Galactic cosmic rays dropped, but they didn't drop in all sectors. They dropped only those had pitch angles perpendicular to the magnetic field. The galactic cosmic rays, who, as we all know, as we all at least learned, were in diffusive equilibrium in the planetary space, and they were omnidirectional. Well, here they were, and they were dropping out perpendicular to the magnetic field. How do they know? Where is the diffusive part? So anyway, we published that in our science paper in 2013, and then, of course, the next time, the CRS group also looked at their data, and lo and behold, they showed the same decreases, as you can see from this plot that Jamie Rankin published in her thesis in 2019, that the same decreases were there. Of course, the pitch and dependence was not that clear there because that was an omnidirectional detector, but you can see the power of the stepper motor, which we never expected would show such a thing. And it wasn't the only time. And if you go on to the next slide, I believe that's the one where I have, I don't see it yet.
But it's on, though.
It's on.
Yeah.
Okay, I did want to show you this slide because what you see on the left is the counting rate as a function of direction, the 360-degree sectors, except, of course, the solar sector, which is blocked. And then in the middle part, you see the fit to that data. You see the curve there as a function of angle and the count rate. And you can see that we get a nice fit. Rob Decker worked on this very much. And from that, we could do a least square fit to 7 of the 8 sectors and deduce a first and second harmonic. But when you write down the anisotropy equation, and when the first harmonic, as you can see from the middle panel, is much, much larger than the second harmonic, then you can approximate the equation for the anisotropy, which you see at the bottom here, and deduce the solar wind velocity. And this is V, the velocity of the solar wind. V small is the velocity of the particle we measure, the anisotropy, and the spectrum, the gamma, which we also measure. That became a very key measurement, especially after the plasma instrument stopped operating after the Saturn encounter on Voyager 1. And this was the only way to deduce the solar wind velocity. And as you all know, it worked very well.
Saturn or Jupiter? I thought it was Jupiter.
No, it was Saturn.
Saturn, okay.
Actually, it failed. It stopped working for a while, and then it came back just. And so we got very good measurements from a plasma instrument in Saturn's magnetosphere. But then after we exited the magnetosphere, it stopped working, which was very, very fortunate that it was after and not before.
Yeah, definitely.
So I don't remember what the next slide was. I think.
Well, it's the plasma flow. Yeah.
No, I finished talking about the flow velocity. Did you click on the next one?
Oh, yes.
All right. One of these times is going to show up on my screen.
Yeah.
Oh, here we go. Now, this is a plot that we did when the American scientist journal asked us to do an article on Voyager, Rob and I. And what we did in the upper right is the velocity in kilometers per second as a function of distance away from the sun and it's kind of plotted backwards, as you can see.
Yeah.
And you can see that at some point the velocity was dropping, and eventually it got to zero with significant errors. And that's what we call the stagnation region, where the radial, this is the radial component of the velocity, essentially disappears. And the question is where in the hell did the plasma flow? Well, go, sorry, where did it go? And that's when we decided to ask the project to do an experiment. And what was the experiment? As I mentioned before, and you can go ahead and click the next slide in anticipation, the stepping plane was pretty much close to the ecliptic. So we asked the spacecraft to turn the spacecraft by 90 degrees and hold it so that our stepper plane would be perpendicular to the ecliptic. And this way, we could actually measure the north-south component. And by the way, just before that, we actually did the paper in Nature where we estimated that the crossing point would be at 121 AU in July 12, and it actually was in August. Anyway,
by a month.
yeah. So what did we find about the velocities in the plane, north-south scanning plane, which is on the next slide? I hope you had already clicked on that.
I did.
And okay, and I don't see it, but you can see it, and you can see the directions, the magnitude of the velocity that we measured, and you see two things. One is that the VN was 3 plus or minus 11 kilometers per second, essentially statistically zero. But you also see that the tangential component was at minus 26 plus or minus 4 kilometers per second. In other words, the theory that was saying that the velocity, that the solar wind would go north was wrong. It went in the tangential direction. So when I remember Len Fix asking me, where the hell did the solar wind go? And and yes, it did go somewhere, and it was in the tangential direction. So I think that that was a wonderful thing. And so next slide is when we had the meeting at APL.
Yeah, but before that, I think in order for you to do that, you had to turn the spacecraft somehow, right?
Yeah, I said that. We turned it 90 degrees.
Okay.
That's where that came from. You missed that.
No,
Maybe I didn't say it very well.
No,
Sorry.
you did. You didn't miss that, but I didn't miss that. But you didn't. What you didn't say, and I wanted to ask, is that was there any fear about doing that? I mean,
Oh, absolutely. It was a risky
so describe that,
proposition.
because
Yeah.
I wouldn't dare touch the spacecraft doing anything.
That's a great question, Kostas.
I know.
Yeah, it was, you tried to do an experiment, design an experiment when the spacecraft was a 35 years in space.
Mm-hmm.
Right.
And you wanted to, you asked the project to turn it 90 degrees and hold it.
Right.
That's something that had never been done before. It had to be on all gyros. And it was a very tough thing to persuade the engineers that this was doable, but they did a terrific job.
Yeah, but
And
the point is that these are not decisions you take lightly. I mean,
well, we discussed it at the SSG, and because that was a big question, where in the hell did the plasma go
right.
if it stopped going in the radial direction? And it was thought worth to do an instrument at 120 astronomical units or thereabouts.
Right.
So the next slide, I don't know if you have seen it already. Yeah, and we met. Merav, you remember that meeting
Yes,
at
totally. That was
APL
wonderful. That was
in
wonderful.
2014?
Yes, yes, yes.
And as you all know, the big issue was, why did the magnetic field stay in the Archimedean spiral direction?
Mhm.
Are we really outside? We were still debating that, and I guess we're still debating it.
I was about to comment that.
And you can see most of the people, some of them who are no longer with us, and the instrument is in the middle there, the backup instrument for that we had the third unit.
Mhm.
Anyway, that was a nice story, and we really enjoyed the back and forth, and it's still going on. Go ahead. I think you're next, Kosta.
Oh, yeah.
And,
Okay, so for something different but relevant, this is the Cassini mission. Uh, of course, as you probably know by now, the Voyager missions are probably the most important mission so far, at least for me and other people. But at that time, 97 to 2017, I would say that the Cassini mission was one of the most technologically advanced ones out there. And you can see this schematic. It had pretty much everything. It had, walking legs, which is the main engine, dancing legs, brains and everything. It had everything, but it also had two sets of eyes, two different sets of eyes. One very good camera, photographic camera, I mean, that you can see here pointing, and a different set of eyes that were part of the magnetospheric imaging instrument, as we call it, the MIMI instrument. It was called Inca, and that's the instrument that you can see here. So that was an instrument that was able to get measurements of what we call the energetic neutral atoms, which are essentially long-distance communicators of what's happening in very large distances away from us, because they participate in an interaction that we call the charge exchange. So when you have an ion gyrating about a magnetic field, and then you have a neutral particle that is essentially unaware of what is going to happen to it. When they come in close proximity, the ion steals an electron from the neutral, it becomes neutralized, and then we are able to measure it at long distances with cameras like that, like Inca, and actually produce images of these processes. So let me show you something. Before we show that, this is a way. Why don't you talk about that? Because essentially that was your paper. Because this is, it's your 2009 paper with Cassini and showing for
well,
the.
I can't see the slide. Have you changed?
Oh, yes, I did. Well, I can
Oh.
start explaining a few things, and then when you see it, you can stop. You can interrupt me. So, because of this camera, in 2009, we were able to sort of combine the information with Voyager and Cassini and take images of the whole heliosphere. And this is where, for the first time, I think you realized that the old model for the heliosphere that looked like the comet should be revised. It's not a
Yeah.
comet anymore. I'm guessing you can see the slide by now.
Yes, I can. And
So go ahead.
we had this schematic that we published in Nature, in Science at the time, and there was a lot of, let's say, unfavorable reaction on the part of the modeling community, because they said everybody knows the heliosphere looks like a magnetosphere and it has a magneto tail and so on and so forth. So I sent the paper to Jim Parker at the time, the late Jim Parker, and he sent me an email. And I don't know if you can see the wording
Yes.
there. I can't, but essentially, Gene was very much prepared to accept the fact, as he said at the very end, we should stop thinking about a long interstellar gaseous wake streaming behind a heliosphere as a local interstellar wind blows by us. And he said, you can read what he said, the inflation of the interstellar magnetic field by the gas from the solar wind drifts across one interstellar flux tube after another. Each flux tube gets a modest inflation of gas from the sun as it's carried out past the sun. So he immediately related to this, and of course later on, when he also saw how strong the magnetic field was when actually measured by Voyager, this became almost self-evident to him, as he told me in person. Okay, well, that's all I have to say about that. It was a revealing moment, and it was made possible by the fact that we had the ENA images from the heliosphere, from the heliosheath, and it was done, way away from Saturn, as you will see later, I guess.
Yeah, I already changed the slide just to show
Okay. Yeah.
a small part of the Mimi team, of the team in Cassini. So these are now, I would say, very well known and very well respected scientists in their fields, mostly in magnetospheric physics. Anna Kotova, Leonardo Regoli, a very good friend of mine, Elias Roussos, Peter Coleman, Norbert Krupp, Chris Paranicas. You can all, I think you can recognize Vytenis Vasilounas there, the person that has his name in a cycle in magnetospheric processes, the Vasilounas cycle, and of course the kappa distributions and everything. Maria Andriopoulou, Nick Sergis, and believe it or not, that's me. Younger. I was younger once. I'm not always the guy.
You still look the same.
No, I don't. I think you look, you see me the same, but I don't. I can spot the differences, and that's you. So that was,
sure.
That was in 2013, and it was pretty much, I'm changing the slide, around the time. Oh, yeah, so ENAs, back to ENAs. You can see this movie. This is from Saturn, and what you can see in this movie are ENAs, I'm going to play it again, rotating around Saturn. So in the middle, it's Saturn, and
Sorry.
this is...
It's not ENAs. You can see the ions in the magnetosphere rotating, which we visualize through ENAs.
I was getting to that. Why did you spoil?
Okay, sorry.
Okay. So essentially, with this beautiful imager, we were able to take these images, these pictures of the processes of ions in the magnetosphere of Saturn, for example, and then visualize them through videos. We can put them in sequencers and get these videos. And it was about the first time we realized, for example, that the ring current around Saturn is rotating, and every time it passes through the midnight sector, it's sort of re-energized. And if I go to the next slide, you can see again this as a paper by Pontus, a key person in ENAs and the heliosphere and Saturn, this ring current rotating. And this is where we realized also that when this ring current energized in the midnight sector, it also inflates the magnetic field. So it creates disturbances in the magnetic field. So these are nice processes in magnetospheres, not just Saturn, but otherwise. And this is the powerful thing you can do with ENAs. And this is when I realized for the first time, because this work about the heliosphere with ENAs was being performed by Tom Krimigis and others at that time, this is where I realized that they were using Inca to look at the heliosphere. So Cassini was right over there at Saturn. The heliosphere is way out there. So this is the sun. This is where essentially Cassini was. And they were using Inca to look at the heliosphere at distances of more than 100 astronomical units, which means 100 times the Sun-Earth distance. And this is, in brief, the process that I explained before. So it was an interesting time for me, I would say, because this is I realized that we can image part of the sky sphere as a whole and study the dynamics of the whole system at the same time. So I don't know, you cannot see that slide right now, but this is essentially from your 2019 paper, from the crossing of the heliopause from Voyager 2. And this is the first time that we combined all the information that we had from Voyager 1, Voyager 2, and of course Cassini in one schematic. And you can see we took note of all the important distances from the sun. So the sun is here at the center. You have the solar system, and then you have the termination shock, which we know that it was crossed at different times from Voyager 2 and Voyager 1. And then we got to the heliosheath, which is this middle region over here. So, and then to the heliopause. So this is the first time we combined all these information. And I think it was way before that. I forgot to mention that at some point, I asked you, I remember that I asked you that it's important to, when I realized that you were doing that work with ENAs for the heliosphere, I said, how lucky we are that we have Voyager and Cassini at the same energies. And then Tom Krimigis comes to me and says, do you think it's luck? And I said, it's not. He said, no, this is careful planning 30 years ago. So I'm saying that because the Inca imager that I showed you before, and it overlaps with energy, partially, of course, with LECP. So
yeah,
what we are able to measure...
Inca is actually goes to much lower energies, but
Yes.
When we were setting the channels, I said, geez, let's make sure that we at least can cover the low energy part of the LECP instrument so that we can have overlap. And that's what made possible the so-called ground truth measurements, where we could see the same energy range on Voyager as we did on Inca and normalize the intensities. And we knew exactly what the efficiency was for ENAs coming from the heliosphere into the
I was so naive that I thought it was pure luck, but anyway, so essentially what we are able to measure with LECP here in situ, we were able to verify everything with the ENAs measured at these distances and with Cassini. So that was amazing. That's a picture that I took actually yesterday. And it's a picture showing the outside of our offices. And you can see it's dominated by Voyager. It's all Voyager all over the place. So that's, for example, that's an old article about the Voyagers, and it has you actually on the cover and a picture of you. I think 2 pictures of you and one of LECP. So you are more famous than LECP, by the way.
I don't.
And this is the cover of Nature Astronomy from the Voyager 2 heliopause crossing, and these are 2 old posters of Voyager. Actually, this one I remember this one from when I was a PhD student when I started back in 2007, and I was thinking, would I ever become a Voyager member? That was way back in 2007. And of course, if I move on, we essentially took on the entire corridor. So everything is dominated by Voyager in the Academy of Athens. And I think nobody cares because essentially everybody loves Voyager, so they don't tell us anything. And we also have Interstellar Probe there. You can see that. And by the way, as I said, I took it yesterday at 4 p.m. So I think, oh, and now we move to the, you can see that?
No, I can see the last one you had, but not the golden record.
Oh, that's the golden record.
I haven't seen it yet. I hope you move to that.
Yeah, it's on.
Yeah, I mean, you all know about the golden record, that's on Voyager, and what you see there is the cover in the middle and the actual record that's inside. And the way that came about, it was the idea of Carl Sagan to have sounds of Earth and so on, and pictures of people and greetings and everything else. And he came to the SSG and in 1976 and said, "Hey, all I need is about 5 kilograms to make this record and the cover, and we'll just mount it on the outside of the spacecraft." And the PIs, at that time we were still struggling with power and weight, especially with weight. And 6 kilograms, we say, hell no, we're not sure we're going to deliver our instrument under the weight guidelines, and we may need the reserves and so on. So the SSG said, no, don't do that. We can't do that. And so Carl went to the NASA administrator and said, look, we need to put a disk on this spacecraft in case it does go all the way and somebody captures it. So the NASA administrator overruled the SSG and said, put it on. So that's how that disk came onto Voyager. It was because of the insistence of Carl Sagan, and of course, how right he was in light of what happened after all these years.
And it just occurred to me, that you're not going to be able to see it right now, but let me show to people where the actual disks are located. So this is where those records are located in the spacecraft.
Yeah, on the side of the spacecraft.
In the side of the spacecraft. So inside that, you have those 2 golden records. The golden record.
It's one.
Yeah, it's one. One golden record.
Just the cover.
Yeah. So yeah, that's it.
Anyway.
Thank you so much. That was fantastic. That was great. I am cognizant that we went almost to the top of the hour. So I'm going to ask if somebody has 1 or 2 questions and for Tom and Kostas, and we can continue this discussion also outside of the webinar. It was perfect going back and forth between memories of you two, but yeah. Nick, you had something to say?
Oh, just either raise your hand or put a question in chat.
I have a question for Kostas.
Yeah.
On the flavor of StoryCorps. How was to be mentored by Tom, and vice versa, Tom? How was to have Kostas as a student?
Okay, so let me start by saying that, there are different types of people leading teams. Mind you, I was always part of a team, either the MIMI team or the LECP. And one of the, I'm not going to mention all different types, but one of those is the ones that lead by inspiration. And Tom Krimigis is one of those persons that actually inspire you to talk to him and listen to whatever he has to say and take it very, very, very seriously and discuss and disagree and have intelligent conversations about everything. So I would say it was challenging throughout the way, but it was inspiring. That's what I mean by challenging, because that's the kind of leader he is. He doesn't rule by an iron fist or a fear or whatever. It's inspiration. No,
Tom,
that's
your chance.
Yeah, well, listen, Kostas, I've been very, very lucky to run into Kostas. He was recommended to me by a friend at the faculty at the University of Athens, and I talked to him, and I realized, first of all, how eager he was to work on data, and I have to say, it has been the chance of a lifetime to find such a hardworking, intelligent. Well, I'm sure I'm embarrassing him,
yes.
but it has been a terrific addition to our team, and in many ways he keeps us going because many of my APR colleagues are involved in 4 or 5 projects, and they don't have as much time to spend on the Voyager analysis. And Kostas has been the person that has enabled us to stay on top of the data. And he has done such a wonderful job, first with Cassini and now with Voyager the last few years. So I consider myself exceptionally lucky to have him as a collaborator.
Fantastic, folks. Great. And Tom, you will be happy. We are revisiting LECP data. Romina is on the call with Kostas, with Matt. So it's an alive, treasure that we go back and look and find new things.
Well, one of the important things, LECP team is actually a team. We have people working with data, like you mentioned, Matt Hill and the deputy PI of our team, and Romina, who is doing phenomenal job in with the LECP data. So I think we have a good line of people in the
it's
team.
fantastic.
Uh,
Folks, have a wonderful rest of your Friday. I know for Tom and Kostas, it's evening already. Anyway, it was a delight. It was wonderful. And I'm so glad we have it recorded for generations to see it and to listen to it. Thank you, guys.
Thank you very
Thanks.
much for
Thank you,
inviting us. It was a wonderful thing to do. Thank you.
Yes. Bye, folks.
Bye. Thanks.
Hello?
Oh,